Okay. Yeah, great. Yeah, thanks for the invite. Today I'm going to talk about speculative decoding, which is a important feature in vLLM. So to be more concrete, I think I will cover like what is speculative decoding, what are different types of speculative decoding, and its performance in vLLM, and some we also, because we are PhD students, we are doing some research around vLLM. So I will talk about some research we are currently doing, and lastly, I will mention like how do you use speculative decoding in vLLM. So what is speculative decoding? So actually, it's a technique to reduce the generation latency. So the intuition is that when you use LLM to generate tokens, some tokens are easier to generate than the others. So instead of using the large language model to generate all the tokens, which might be quite expensive, you might want to use some small language models to generate those easy tokens and large language models to generate those difficult ones. And it has a very good characteristics. It's lossless, so you can use it like safely without like affecting the accuracy. So let me give you a concrete example, right? So on the left-hand side, like it's a like normal generation. Basically, given a prompt, you generate T1, T2, 3 auto-regressively. So you generate T1 first, then T2, then T3, right? You generate token one by one. But with speculative decoding on the right, what you will do is normally you will use a small model, like to generate those tokens, like to propose those candidate tokens auto-regressively. So here you generate T1, T2, T3 prime. So you say, oh, the answer might be T1, T2, and T3 prime. And then you send those tokens for the large model for verification in a single batch. So you send the T1, T2, T3 prime to the large model, and large model will tell you, oh, T1, T2 is correct, but T3 prime is incorrect. So the correct answer is T3. So notice here that a single forward pass of the large language model, you verify like kind of 3 tokens. So here you, in a single forward pass, you generate 3 tokens, T1, T2, T3. So compared to the normal decoding, like you run the forward pass once, you generate 1 token. With speculative decoding, you call the large model once, but you generate more than 1 token. So in that case, it can reduce the generation latency. So this is a very high level like description about the algorithm of speculative decoding. But vLLM is a system with continuous batching. So basically, vLLM will batch different requests in a single batch so that it can increase the system's throughput and utilization. So how does speculative decoding work with continuous batching? So on the high level, we will have 2 runners in vLLM. The first one is the draft runner. So basically, the draft runner is responsible for running the small model. And we will also have the target runner. So the target runner will be responsible for running the large model. So as shown in the picture here, right, like given the request in the request pool, so we will have a draft runner to propose tokens to run the small model auto-regressively, like step by step. And we will send those proposed tokens to the target runner to run the large model. So the large model will verify the correctness of those tokens in a single forward pass. And lastly, it will decide, oh, which token is correct, which token is incorrect, which token is accepted. And it will also generate 1 extra token, yeah. So we implement speculative decoding in vLLM because we think that latency is a kind of important feature, important metric. So we want to reduce latency, so we implement speculative decoding. So the way we implement it is we change the scheduler in vLLM so it can schedule more than one slot for the tokens because you are generating more than 1 token in a single forward pass. So you need to change the scheduler. At the same time, we change the memory manager. So we will manage the KV cache for both the draft model and the target model. We will have the speculative decoding worker, which is responsible for calling the draft model to draft the worker to propose tokens. Call the target worker to verify the correctness of the tokens. And lastly, we have the rejection sampler, basically to finally decide which tokens are accepted, which tokens are not. So we try to make the speculative decoding framework as general as possible in vLLM, so it can support like different types of speculative decoding methods, which I will discuss more later. So the first type of speculative decoding in vLLM is draft model-based speculative decoding, which is also the most commonly seen speculative decoding, like standard speculative decoding. So the way we do it is we use small model to guess the tokens, right? We say, oh, the next 3 tokens might be something, and we launch that large language model to verify it. And there are some commonly see draft target model pairs. For example, we can use a Llama 68M model to speculate a Llama 7B model. We can use a 7B model to speculate a 70B model. But as a user, you might have a question like how do I pick the draft model? Right? You don't want the draft model to be too large, because running the draft model may cause some overhead. At the same time, you also want it to have a good accuracy. Basically, you want to have a good speculation accuracy so that you can get better speed up. So the challenge here is, how do we find the draft model? So actually, we find it's a tricky question, because, for example, we haven't found a very good draft model for the Llama 3 8B model. The reason is we cannot use the draft model we use for Llama 2, because Llama 2 and Llama 3, they have different vocabulary size. And the speculative decoding requires the 2 models share the same vocabulary. So it's a real challenge, right? How do you find the draft model? So because of this challenge in vLLM, we also support different types of draft model-free method, draft model-free speculative decoding. So the first one is prompt lookup decoding. So prompt lookup decoding is the first type of draft model-free speculative decoding. And it's also pretty simple. So I can just give you a quick example, right? For example, given the prompt, what is the capital of South Korea? You want to generate tokens, right? So the way you generate it is when you see the prompt, you will build a lookup table. So here the lookup table is all possible 2 grams, right? What is the capital of, and also the speculative tokens, right? For example, when you the 3 tokens after what is a capital, the 3 tokens after is a capital South, right? So you will have this lookup table once you receive the prompt. And during the generation phase, when you already generate 2 tokens, the capital, right? So you will check the lookup table and you will find, oh, there is a match here. So we already generate, we have the key, the capital in the lookup table. So for the next 3 tokens, you will just use a value, you just look up to propose, right? You will say, oh, maybe the following 3 tokens will be the South of South Korea. And in the example here is correct, right? So the 3 tokens followed is just of South Korea. So the intuition behind the prompt lookup decoding is that for some workloads, for example, summarization, document question answering, so there is a big overlap between the prompt and the answer. So instead of using a small model to propose token, to guess the tokens, you can just use a prompt, use the information in the prompt to speculate, because there is a big overlap between the question and answer. So sometimes the large model, it just repeats the question. So we find that prompt lookup decoding works for some, as I mentioned before, summarization, question answering data sets, but they don't work for online chatting, those open question answering, those type of data set. So it's really workload dependent. But for summarization data set, question answering data set, sometimes it can achieve really good speed up. Yeah. So another type of speculative decoding, which is kind of popular, is Medusa Eagle. So this type of speculative decoding is saying, oh, instead of using a draft model, or instead of repeating the words from the prompt, maybe we change the original large model, but we just add some heads, we add some layers to those models. So this example here is that so they change the original model, they just get the hidden states of the last transformer layer, and they send it to some they call it Medusa heads, but basically it's just some extra layers, and they use those heads to predict the tokens. So the intuition behind this method is that we believe that large language models should have the ability to produce more than 1 token at a single forward pass, right? So instead of having another separate model or some other methods, we can just add some layers to the large model to let it produce more than 1 token in a single forward pass. So this is the high-level intuition behind those type of methods, like they add some extra layers to the original model to propose tokens. So we have a preliminary integration in vLLM of those methods, but to really achieve good speed up, it needs some like efficient kernels. So that's why we are also working actively with the community to further improve the performance of those type of speculative decoding. So after going through all type of speculative decoding support in vLLM, so what's the performance look like? So the first performance I show here is a draft model-based method. So basically, it's a Llama 370B model of shared GPT data set with 4 H100. So the x-axis is a different QPS, the y-axis is end-to-end latency. The blue bar is the method with speculative decoding, and the red bar is original, right, like normal decoding. You can see that like it can achieve like up to 1.5x speed up at QPS 1. And this is for like n-gram, right? Because as I mentioned before, like those prompt lookup decoding, like, or we call it n-gram, like prompt lookup decoding works better for like summarization data set. So here we use a CNN Daily Mail, like summarize a Daily Mail data set, and you find that it can achieve up to 2.x speed up, like when QPS is low. But that looks really promising, but that's not the end of the story. So actually, I didn't show the full picture in the previous slides. So here I show the full picture. So basically, we find that after we implement speculative decoding, we find that it might not always be beneficial. So this is a full picture. And the QPS, when QPS is 10 or 8, when QPS is high, we find that actually speculative decoding slow down the performance. So the intuition here is that speculative decoding trace some extra compute, right? Because you propose tokens, you verify it, so you use a draft model, and also if the tokens are not accepted, you are wasting some compute, right? So basically, you are using some extra compute for reduced latency. So when the QPS is high, when the system is already compute bound, when the GPU is already pretty busy, you don't really want to waste those compute. So if you, at the time you use all the compute for normal decoding, you might achieve better performance. So that's a high-level intuition behind the slowdown. But the high-level takeaway here is that we find that naively implementing speculative decoding is not enough to make this feature really usable in a production setting. To make it the feature always good for the users, we kind of need need some other like methods, need a mechanism to tune this feature automatically, so that the users can use this feature safely, like to always improve the performance. Yeah, so this is the intuition behind the slowdown, right? So like the example here, so given the 3 requests like x1, x2, and x3, and the proposed length is 2, right? So on the left picture, if you do speculative decoding, because some tokens might be incorrect, so here you are, you generate 4 tokens, but you can actually, what you compute is you compute 9 tokens. So you waste 5 compute here, right? Like so in the low QPS it's fine, but in the high QPS, the waste of the compute might be quite expensive. So instead of doing speculative decoding on the right hand, you can just do normal decoding. In that case, you generate 9 tokens with computing 9 tokens. You don't waste any compute here. So that's why, so this motivates some research around vLLM speculative decoding. So we are saying that, we find that speculative decoding works for low QPS, but not good for like high QPS. So we want to dynamically adjust the proposed length, adjust the degree of speculation based on like the system load and the speculation accuracy. As I mentioned before, it's a continuous speculative system, right? So currently we are doing global proposed lengths. Basically for different generation steps, you propose the same number of tokens, but actually you can do more finer granularity, like basically step level. For different generation steps, you have different degrees of speculation, or even different requests, you can speculate different number of tokens. So yeah, I encourage you to check out our paper for detail. But on the high level, we will you can just look at the graph. Like when the system load is high, we will propose less tokens, we will speculate less tokens. And also when the draft model is accurate, right? Like if it has high accuracy, high acceptance rate, you can like the degree you reduce the proposed length is less, right? It's lower. Yeah, but with this feature, so we will integrate this feature in vLLM. After integrating this feature, hopefully the users can turn on speculative decoding feature safely. So which means no matter how the workload look like, no matter what's the QPS query per second, we can always achieve a speed up with speculative decoding without degrading the performance. And lastly, I want to mention like how to use speculative decoding in vLLM. So actually, it's pretty simple. So you just need to launch a vLLM server, right? So like vLLM serve here like a 17-bit model with TP4 tensor parasites 4. Those are the commands you use for like for launch a normal server. But if you want to add a speculative decoding feature, you just add those flags. You want to say, oh, this is my speculative model. This is the number of tokens I want to speculate. And here we also specify what's the tensor parallel size for the speculative model, because the small model is small. You don't want to do like you don't want to distribute it across different machines or GPUs. So you can say, oh, maybe for the draft model, we just do tensor parallel size 1. So this is for draft model based speculative decoding, but we also support like n-gram spec decoding. In that case, the speculative model is just n-gram, and you just need to specify like how many tokens you want to speculate. So after the integration of dynamic speculative coding, we want to even get rid of the number of speculative tokens. So basically, we will tune the speculative tokens for you automatically within the system, so the user does not need to like specify it explicitly.
A quick question about the n-gram speculative implementation that's in vLLM.
Mm-hmm.
If you say num speculative tokens, are those 4 tokens treated as a single batch? So in your example, it was of South Korea.
Right.
If the of and South were correct, but Korea was false, do you still get the hit, or do all 3 have to hit in the speculative tokens for it to be a hit?
Okay, yeah.
And to get a performance improvement.
Okay, great. Thanks for the question. So the example here, all 3 tokens are hit. But sometimes you might say, oh, what if it's out of South Africa? So in that case, you still get two tokens, right, in the beginning. So it's the number of tokens you get is just the longest prefix. So
okay, so there's a performance implication of increasing the number of speculative tokens, but not but you're not potentially losing out on hits by increasing the number of speculative tokens.
Right, you are right. But the trade-off, cool. Yeah, but the trade-off here is that you cannot make the speculative tokens like say 100, right? Because when you verify those tokens, you want to know if those speculative tokens are correct. You verify them, you still need some compute. So if the number of speculative tokens is like very big, like verifying the correctness will be very expensive. So yeah, so you want to tune it in a like to be a good number, like because you need some compute to do the verification.
Yeah, can I also ask a question regarding this? Do you have any benchmarking for the different number of tokens here for n-gram?
Yeah, we have that in the paper. You can check it out. But in the slides, it's only like we kind of manually tune it, like it's a good number. But you can imagine, right, at low QPS, you have lots of free compute. Like so, in that case, you can speculating more tokens can give you more speed up. But in the high QPS, because you don't have that many free compute, speculating more tokens might slow down the system. So like at QPS 1, the best speculation length might be 10. QPS 2, the best speculation length might be 8. And QPS 3 might be like 6. So you need to adjust it like according to the system load. Yeah.
Yeah, and is that covered by this dynamic logic?
Yes.
Okay, cool, thanks.
So you would choose like different n
Yeah. So I think it will decide two things. First is at different system load, what's the best speculation length? Like how many tokens I speculate. So that's the first thing. And the second thing is when to turn it off, right? Because we find that when a system is already computed, but maybe you should just not use speculative decoding. When to turn it off. So I think those two main features that dynamic speculative decoding provide. Yeah.
And when you evaluate the tokens, how do you blend like essentially you're blending like prefill and decode. So do you heavily rely on like chunk to prefill or?
No, so currently speculative decoding only work for decode. So we don't do speculative decoding.
But you still need to like evaluate the like chunks of contiguous candidate tokens.
Right.
But that happens in like a decode job?
Yes, that happens in the decode path, but in a single forward path, you verify it. You are saying a chunk of tokens, right? Like multiple tokens. Yes.
Okay.
Yeah.
And then you just like throw away the KV cache. That's not like for the tokens that fail.
For tokens that fail, you throw away the
like truncate the KV cache.
Yeah, truncate the KV cache.
Okay.
Yes.
There's actually a question in the chat. Does the default setup for speculative decoding in vLLM work with phase splitting, i.e. draft model and target model running on separate GPUs running concurrently?
Oh.
Or does it always does the draft model always interrupt target model execution?
A great question. So currently it's sequential. So so when the draft model is running, target model is blocked. So basically it needs to wait for the draft model to finish before it can do the verification. So yeah, we think about like asynchronized, like basically the draft model keep running, the target model keep verification, but it will make the engine more complicated. So that's why currently it's still like sequential. Yeah.
Do you think that would be through like kind of like a disaggregated prefill like system or maybe something different?
Yeah. So actually many people ask these questions. So currently the draft model and the target model, they sit on the same machine, they sit on the same GPU, like almost the same GPU, right? They have the same TP. So what you are asking that is that possible to run the draft model and target model on different GPUs or even different machines? So I think it's possible, especially we find that if you have domain specific draft model. So for example, you will have a draft model for Lily, a draft model for other people. So in that case, it will improve the token acceptance rate, right? Because the unique tokens Lily say is very limited. So it's very easy to speculate Lily's Lily's generation. Mm-hmm. So basically, if you can have a domain specific draft model, it can further improve the performance. And in that case, you need more than one draft model. So you might want to distribute them on different GPUs or even different machines. But still, like the system design, system architecture will be very different from what we are currently doing now. So I think disaggregation preview will be the first step, because it's the first step to separate the engine on different machines. Once that is more mature, we can think about like how to like integrate like those type of speculative decoding architecture on that part. Yeah.
Okay. There's another question from Edward. In our system at Positron, which is similar, our model has been set to a target number of tokens to feed the evaluation model because we have a good way to estimate the attention cost for those to evaluate and then speculate enough to expand the continuous batch up to get up to the sweet spot, which seems like they target, like batch 8 or something, I think. Yeah, maybe that's just like a simple threshold policy on the...
Mm-hmm.
Yeah, it just worked out well for us that we could just sort of use it to bring the usage up to wherever the sweet spot was for the ratio between attention and the rest of our feed forward.
Yeah, but you still have to deal with like prefill, like coming in or
yes, prefill slam, some continuous batches here and there, all that. Yeah, but if I have an otherwise idle batch, then I may speculate quite heavily during that run.
Yeah, that makes sense. That's a simple heuristic. Okay, there's a few more questions, but maybe I could go through the rest of the slides and then we could go to the final question section. If you want to pass over the share. Yeah. Yeah, so we'll continue on just like a summary of slideshow button on what's new in vLLM over the past 2 weeks. So there was a pretty big release, 0.6.2. This came out with day 1 or day 0 support for Llama 3.2 models. There's also, as I mentioned, this sort of ongoing work for pulling out beam search and seeing how we want to reimagine it inside of vLLM while still supporting our users that depend on it. There's lots of other models like the Solar Pro series of models, Mini CPM3, Lava 1 Vision. So increasingly seeing a good variety of vision language models support inside of vLLM. And then there's been a good bit of support in supporting features like pipeline parallelism for vision language models, function calling for more models like Mistral, actually through the official Mistral library with the Mistral tokenizer and Mistral inference, and then expanding bits and bytes support as communities been using that more and more. On the hardware side, there's basically ongoing improvements for TPU, in improving performance there with the multi-step scheduling, CPU performance and expanding vision language models on CPU, and as well as AMD, adding more performance for attention and lessening the impact of KV cache quantization. On the engine side, we're starting to see some introduction of more advanced scheduling. So adding priority scheduling for requests. So some requests can be scheduled at a higher priority than other ones, as well as better tooling around the multi-LoRa support. So we, I believe, can support, adding LoRa or attaching new LoRa modules over time and understanding maybe how long they're used during serving. And then a big feature for a while is for like the LLM, offline LLM chat interface. So LLM.generate probably. Now there's a chat interface, so you don't need to mess around or be aware of the Hugging Face transformer, tokenizer, and apply chat template. You can just use the usual chat templating you use with transformers or effectively in the OpenAI API, and which we added in a previous release. But now you can add batches of chat templated requests, which we've definitely found useful for synthetic data generation. On the performance side, there's the MQLLMEngine, which we'll go into detail on, as well as many improvements to multi-step scheduling as we want to enable it by default in upcoming releases for better performance. And then, we've been expanding CUDA graph support for more use cases, and particularly for encoder-decoder models came out in this release. And then I'll say kind of lastly, there's been really great progress on Torch Compile as we work towards Torch Compile full graph support, and our custom passes for using, quantized, essentially quantized, dequantized operations in vLLM. So I'll go through the top 3 features we identified. So you can use the new Llama 3.2 vision models in vLLM. Currently, they require a good bit of a large amount of KV cache due to some inefficiencies we have with the KV cache page sizes. So do beware of especially tuning down the max num sequences. You should be able to fit it on pretty small GPUs with just the max num sequences of 1. But you can also try decreasing the maximum model length, as it is 128K by default, which can be pretty large for smaller GPUs. Text-only inference is also supported with them. It's essentially equivalent to the base 8B model and 7B model, and performance is essentially the same there. And currently at the moment, we don't support multi-image support, but this is definitely a high priority feature as we work on also improving the performance. So we have an example here of how to use it in the offline interface. It's pretty simple. And then I've been busy making starting to make some quantized checkpoints for this. So you can find FPA checkpoints that you can run on A100s or H100s to fit them on less GPUs. Another big development, sort of on the stream of performance enhancements that vLLM has talked about with the 0.6 release, is the MQLLMEngine. This is kind of a silent improvement, as when you're using the OpenAI API server, this is now just used in place of the usual async LLM engine. And basically the story is, hopefully you know that we pulled out the API server, which was using fast API with Unicorn, out from the engine. So dealing with the HTTP requests and all of that in user space and networking space is pulled away from the engine onto another Python process. So they're not competing for resources. But we still found overhead in just comparing the async LLM engine to the LLM engine, because we have so much use of async IO, which allows for concurrency inside of Python. But due to the global interpreter lock in Python, you're still only getting basically single thread performance in one process. So we basically decided to replace the async LLM engine with MQLLMEngine, making a new process where all of the scheduling and accepting requests and returning tokens back to clients are, specifically really either through the offline interface or through API servers. Using 0MQ, which is the same library we used for the API server. So now we're pushing and pulling from these essentially 3 separate processes, one for the core engine that's running the model forward passes, one for the scheduling of new requests and returning to the API server, and then one for the actual API server dealing with the networking requests. And we found, particularly on slower CPUs, this can improve performance in single step, which is the default setting in vLLM currently, by 30%. And in multi-step, it can even show small performance enhancements, just reducing the overhead there. So this should hopefully just be transparent, better performance for everyone who uses the server. And then another thing I wanted to call out is, we've had several RFCs and discussions with the community on Beam Search, as it's a very complex and kind of underused sampling method currently. And we, opened the initial RFC for dropping Beam Search support, and we got a lot of feedback that there's a lot of users in the community and also enterprise companies that use Beam Search for their products, although they use them more in an offline capacity versus an online serving capacity, and they're less concerned about performance. So we've still decided to essentially pull it out of vLLM's core sampling loop and scheduling and re-implement it external to vLLM, and actually make use of some of the features that vLLM has, like automatic prefix caching, to see if we can implement this efficiently. Essentially what we found is, if you externalize Beam Search and just pull it out of the error loop, then you do see a performance drop. Here on the right, we have some benchmarks, the old one getting 0.6 requests per second, and then the new external Beam Search getting only 0.1 requests. But if we enable prefix caching, which basically means requests that are running with shared prompts, shared sections of the prompt, will not need to recalculate the prefill and can use existing KB cache pages that are in memory. We actually see a performance improvement over the internal Beam Search, the internal Beam Search method in this throughput scenario. So yeah, we're excited about this sort of basic development. And we've enabled this Beam Search API for the offline LLM class, and we'll be working on adding some support for the serving interface, so people can still get some usability there, especially as we start to enable prefix caching by default and deprecate the V1 block manager. But definitely, if you have any use cases on Beam Search, please join these RFCs and let us know your use case, so we make sure we're still serving you well. Okay, and now we're all open for discussion. Feel free to ask lots of things. Seems there's been a lot of discussion in the chat.
Yeah.
So yeah, are there some questions you want to talk to specifically, Lillian, or?
Is anyone else going? Otherwise, I can go ahead.
Yeah, sure. Go ahead.
Yeah. Hi. I have a question for Lily. So, so what do you mean by it's only done for decoding? So for the pre-fill stage, for both of the draft runner and the target models, are those like done in separate cycles? Because like they're two different models now, and you would have two pre-fill steps for both of them separately, right? And then this decoding starts.
Yes. I think it's more engineering. More implementation details. You can also do it for pre-fill. But you are totally right. So when you have two models, you need to run the pre-fill for the small model. You need to run the pre-fill for the target model. Basically, you will generate the KV cache for both models. Yeah.
Okay. That is a step like that can happen at the same time, or
it's sequentially. So basically, you want.
Or it happens sequentially. Okay.
Yeah, run the pre. So currently, all the implementation in vLLM is sequential. Basically, you run the draft model first, and then you run the target model.
Couldn't you have pipelined requests?
Yeah. Actually, you can pipeline. So you divide the batch. You divide the single batch in two batch, right? And then, so you send one batch to the draft model, and then send one batch to the target model. But when the target model is running, the draft model can run this. Run the second batch to do the.
Basically, what I'm thinking is you have so basically we believe the target model is the best thing out there, right? So whenever the draft model beats the target model's time to generate a token, only then we pick speculative decoding, and then we see if that is the one that it has generated. Basically, if you think about in execution time, its speculation is done based on if it comes first or not, kind of thing. But that would require it running parallelly and not sequentially. So that is also there.
It's just the system will be more complicated. Yeah, but I do agree. If you do pipelining, you can kind of improve the utilization for the target. For the GPU, right? Because it can keep running a large model.
Okay.
This pipeline parallelism or more like mini batch?
Mini batch.
Okay.
You just divide
nanoflow.
Yeah, you just divide the sample batch into two batch.
Yeah. And that would be perfect for speculation.
Exactly.
Yeah, that's what I kept thinking. And then she said she does it only for decoding, and I'm like, okay. Then I changed my entire because I thought this was happening. And then I had to rethink the entire thing. Okay.
Yeah. It's really complex. If you haven't seen the nanoflow project,
not aware of that.
It's
okay. I'll check.
Yeah. They show this as how to get maximum throughput. They show beating all of NVIDIA's benchmarks and things for sort of maximum GPU utilization by essentially breaking out batches into mini batches and pipelining operations that are memory bound with ones that are more compute bound to try and get compute bound all the way. But it results in very complex C++ code for everything to get it right. So it's hard to get it in a production system, but it's very impressive for an academic project. And definitely put some questions on could we get some cheaper alternatives to that to get closer to that level of performance. It's definitely topic.
Yeah, the best way would be to get better at the lesser reducing the rejection rate, and that's what I think you had mentioned in the chat at fine tuning and all that. So that works essentially. Yeah, cool. Thanks, sir.
Yeah, there is one question about how we deal with rejection. How do we deal with the KV cache of the tokens that are rejected in vector code? So actually, in vLLM, Michael can correct me if I'm wrong. So for every step, you generate some tokens. then you append those tokens to the sequence. So basically, you tell the sequence data. You say, oh, those 3 tokens are generated in this step, and this is a KV cache. You also append it to the block table. So this is the KV cache correspond to those tokens we generate at this step. So in speculative decoding, so if some tokens are not accepted, so you just basically don't append to the sequence. So basically, you don't mark them as a tokens that you generate as a current step. So you don't really like invalidate the KV cache, because after each step, you only append the valid tokens and its corresponding KV cache into its corresponding block table and into corresponding like token IDs. Yeah. So basically, you only track the tokens you accept at each generation step. Yeah. And for those tokens, the KV cache, for the tokens that are not accepted, you just don't add the mapping. You don't add the mapping to the block table. You don't add the mapping to a sequence. So in the next iteration, like it's still visible to a scheduler. So other requests might override the KV cache of those like rejected tokens.
Yeah.
Not sure if I explained it correctly.
No. Yeah, I think that's correct.
Yeah.
There's actually a question here which you asked me, which is like, what are some easy indicators to measure to detect when a GPU is memory bound or compute bound?
Yeah, I asked Michael 2 days ago.
Yeah, and I didn't give a satisfying answer. I can say it's difficult. But I mean, one thing for sure that's like something we could do for like essentially the cost of a little bit of extra startup time is essentially run like a few benchmarks or just like forward passes of different numbers of tokens through, or different M. And you can just see like when the decode time starts to be or like when the forward pass time starts to grow. Because and like what you'll essentially see is like it'll grow very like slowly until you get to like maybe M like 64 on like an H100 or something like that. Yeah, and this is sort of like an empirical way to know like, okay, what kind of M or what number of batches or number of tokens are essentially free from a forward pass perspective. Because if you're memory bound, you're just going to be bounded by the memory bandwidth that you have, and then you won't start seeing that you're compute bound until your time starts growing essentially linearly with the amount of compute you're adding. So you can essentially look for when's the first time that like the forward pass time like doubles, then you're probably in a compute bound scenario, and you're going to start scaling just upwards with the amount of new tokens that are being added. And there you can just get a rough threshold for, okay, I'm only good up until batch 32 or 64. Yeah, but definitely don't believe the data sheets. It's hard to achieve peak theoretical flops. You do need to do measurements, is my opinion.
Yeah, so from what I talked with Michael 2 days ago, I realized that that's Michael taught me. So basically for different layers, because there's different kernels. So the point, they shift from memory bound to compute bound are different, right? Like for example, like FFN and attention, like the shifting point might be different. So it's very hard to say our current system, current engine, is it like memory bound or compute bound because it's multiple layers, different operators.
Yeah, like layer norm will always be memory bound.
Yeah, exactly. So but after going back and think about it, maybe I will just use the LLM like engine class. So basically, I will send it to batch size 1, batch size 2, batch size 3 until like batch size like 100 or like 200, and then I look at the throughput, like how many tokens the engine can generate, and you will see that the throughput grows up until some batch size it will plateau. So at that point, I say, oh, roughly, maybe that's a point we are kind of compute bound. Yeah, so that's an easy way if I test myself. Yeah.
I've seen something similar to what you're mentioning with throughput, also with intertoken latency. And I actually wanted to ask that question is, I've been experimenting with sending different request rates to a model, both on quantized and unquantized model. And at some point you start seeing intertoken latency is stalling. It's getting really, really slow. And I actually the question that I wanted to ask is, when I've been doing this on FP8 models on Lovelace hardware, I see that the intertoken latency is actually worse with once I start hitting request rates of like 5 to 8 to 10 requests per second than it is with the unquantized model. I wonder if you had any insights as to why that might be, because that was quite surprising to me.
I see that as well in our testing here at Cancel, that we at high load, the quantized model actually does worse in terms of responsiveness on the request.
Okay, there's quite a few more questions. So I'm happy to stay and keep answering questions with people, but we'll go through the sort of closing notes. So yeah, thanks very much for joining and for enjoying Lily's talk with us. So definitely, welcome to the vLLM community. If you're new here, if you're not new, thanks for coming back. We always welcome contributions, for new algorithms or research ideas, or even just practical features like sampling, or new hardware backends. So definitely, check out Good First Issues, or, essentially the tracking issues or RFCs for features you're interested in, and, talk openly about it, leave comments in the issue, talk to people on their PRs. This is how, you get to know what people are actually working on and what you can help with. Also, give us any feedback on office hours, so we can keep changing and tuning it to better serve you. Hope you enjoyed these talks. And yeah, we just came from Ray Summit earlier this week. It was a great conference. It was great to see a lot of, real enterprise users, both using Ray and vLLM. And we had, great talks from, like Uber, Apple, Intel, Alibaba, who shared how they use vLLM within their companies. We'll be doing like future events in person. So we at Neural Magic and maybe some vLLM committers will be at NeurIPS in December. And then of course, make sure to go to any of the vLLM meetups that get announced on their Twitter page or on the vLLM GitHub if you're nearby. And then join our webinar on October 24th to learn how we at Neural Magic help enterprises be successful scaling out vLLM on their infrastructure. And also, if you're looking for a job to work on vLLM, we're hiring people all the time, and would be happy to talk with you.
Can we do one thing before everybody leaves? I would love to take a team picture. Is there anywhere, if you're comfortable, if you just want to pop on camera and just wave, give us a peace sign, whatever your thing is. Yes, Devin, let's go. Nice. I bet it. I'm going to take a quick picture. I'll give you 10 more seconds. I would love to take one. We're finally getting in person, and this is becoming quite a community. We're pumped about it. Oh, look at all these people on camera. Nice. Jeannie from Neural Magic, this was your idea, and you're now on camera. Come on, Jeannie. All right. And Michael, can you take a screenshot as well? Will you get a second?
Yeah.
Yes. Anna, I love the heart. Thank you. One more. Yeah. Perfect. Thank you guys so much.
Okay, thanks everyone. That's the majority of the talk, but I'll still go through some of the questions, and feel free to ask directly if you still want to talk. So,
I just have a quick question for Lily. Is it so about because it looked like the way people were choosing draft models was they were just going to Hugging Face and trying to find a usable one. But is there any is there any, because I was just thinking just take the first model and then do one of the many algorithms or methods out there that exist to just make it smaller. So knock out some of the weights or something and then just use that. So is there any academic reviews? Because then you could also fine tune it too. So you could say, okay, this draft model isn't good. Let me go back and sparse it less and make it slightly bigger.
Yes, exactly. There are some work called self-speculation. So basically, you just use some layers. Let's say you only, like the large model is 70 layers. You only use the output of the first 10 layers to speculate like the following tokens. But from my experience, for those type of work, you still need to you still need to add one layer. You like add one layer to align the output of the first 10 layers with the output of the last layer. So you still need to align a little bit. It's not like fully like training free. Yeah. But yes, there is a line of work doing like self-speculation. Yeah.
Yeah, that does seem like the next step would be just then self-speculating, just doing it all in one step, not even having to go out to train anything new.
Yeah, we want someone to contribute it to vLLM. We don't have the bandwidth. So if you are interested, please contribute the self-speculative decoding to vLLM. Yes.
Yeah, I saw some discussion on like quantized models and like performance. I'm not sure if it's like accuracy or inference performance, but it definitely, there's like a broad range of quantization methods and like how they impact your accuracy or impact your runtime performance. So yeah, definitely like happy to talk with you directly and learn like if you're using the right method for the right thing you're looking for. But definitely it's not the case that quantization is like always a loss. Definitely for things like FP8 with dynamic scales, we see, nearly lossless performance. And we're actually going to be releasing a blog soon going over where we did, I think, over like 500,000 evaluations across different quantized checkpoints. So we're going to go really in depth and talking about how different methods like weight-only quantization and activation quantization that will help to dispel this a bit. But definitely there's a lot of bad quantization methods out there. So definitely the things that you can look for is look for fine-grained quantization, which means like not using just like per tensor scales or maybe even channel-wise scales or really static scales for activations. You usually want to have some sort of dynamic quantization for your activations if you're worried about accuracy. This maybe doesn't show up as small, relatively simple evals where you're just focusing on prefill. But when you're focusing on evals that require a lot of generation and particularly long context, having sort of dynamic activation quantization is really important for making sure that your evaluation metrics don't drop at those really large activation sizes. Yeah, so that's what I'll say on that. Yeah, there was maybe some back and forth on MQA kernels to replace batch expansion. Oh, Lily, you're on that.
Yeah. So
I saw some PRs for that, but I'm not up to speed.
Yeah. So that one is so for that one we didn't change the scheduler at all. So the scheduler is the same. Like the output processing is also the same. So we only change we just remove the batch expansion from the and use a flash attachment kernel to verify it. So the scheduling logic and the output logic, they are exactly the same. We only change two parts of it. The first is we prepare the input, right? Originally you prepared one token for each request, but now you need to prepare multiple tokens for one request. So that's the first place. And the second place is the backend, right? Like the backend needs to know, okay, those three tokens are for the same request. So in those three tokens are for the second request instead of one token for each request. So that's we change the backend a little bit. So that's why we change the flash attention kernel backend a little bit. So that's why it only supports flash attention backend. But for all the other parts like KV cache, management, or scheduling, they're actually the same.
Yeah. I just wanted to, Robert Fisher, maybe if we just talk on Llama 8B, usually we don't recommend or see, usually we kind of deploy that on a single, mid to large scale GPU, like an A100 or H100, or maybe at most TP2. But you actually even see these particularly before some of the CPU overhead optimizations, you would see even unquantized Llama 8B on two H100s would get worse latency than running on a single GPU. Obviously here you're comparing quantized versus unquantized. there's some additional, maybe there's maybe like relatively more distributed or like kind of collective communications that happen when you have a quantized model with that much tensor parallelism. But yeah, I guess is there like a reason why you're deploying like a small model across like that much tensor parallelism? Is it like a really heavy like batch load?
No particular reason, except that's what the hardware happens to be. The plan at this point is to do the same kind of testing, but using the process parallelism instead of tensor parallelism, since you can deploy basically the single quantized model onto the single A100 40 gigabyte. Then
Yeah. I would expect that to definitely give more like throughput performance because you can actually like, have multiple requests running on the different GPUs as they're passing through the layers. But definitely happy to go in depth with whatever you have to share.
Yeah. Let's see if you want to just grab some time. I'm happy to run through what the testing was that we did, just so you're aware of it. But it sounds like it's not a surprise to you.
Yeah. Unfortunately, like there's definitely, splitting out models can be complicated.
Yeah.
Thank you so much, Willard.
I need to go, guys. But if there are any questions, you can send it to me or send it to Sasha or Michael and route it to me.
Yeah.
Answer. I just have a conflict.
Yeah.
Yeah. Thanks for those questions.
Thank you so much, Willard. That was awesome. See ya.
Slowly.
A question from Sandeep on how to combine the MQLLMEngine Racer. I'm not sure like the exact interface like Racer has to vLLM personally, but certainly if there's an integration now for the async LLM engine, it should be very similar to integrate it with the MQLLMEngine. And I would just recommend looking directly at the MQLLMEngine PR that shows how to rip this out in the API server we have now and replace that. Generally, the MQLLMEngine, the reason why we like kind of focus on it is like it's really easy to shoot yourself in the foot with the async LLM engine because of all the async IO usage. So we actually use like the MQLLMEngine like internally in Neural Magic with like integrations into other server front ends. And it's been a lot easier to integrate the MQLLMEngine and get better performance in essentially like server orchestration front ends that require custom integration. So please look at the PR and leave comments or questions like directly there, and we can get back to you there. Maybe I'll share a quick link to the PR there. I can find this.
Yeah, that would really help actually. So we, as you said, like we are using async engine as of today's for few of our production workloads. As you showed the reports and the benchmarks, right? I mean, we are seeing around like 30 requests per second, token generation per second, right? Probably if this multi-step new engine helps us to increase the tokens generation speed, I think probably we can try this out.
Yeah, definitely would recommend using multi-step as well. If you can, multi-step is still a bit like early. Like we're just adding support for like chunked prefo with it. So if you're using a lot of the other serving features of vLLM, multi-step particularly is still like a bit, multi-step scheduling is still a bit maybe underbaked there. But it definitely helps on systems with weak CPUs where you're really sort of getting a lot of overhead there. I think those are most of the questions in the chat. So yeah, are there any more from the crew here? Sounds like no. Yeah, thank you all very much. Or wait, Mohammed, you have a question?
Yeah, so maybe just applied that it would be better if we find out more models for the draft and data. So any idea or any example? Because for example, I'm using Llama 3 point to the 3 billion one for the draft model and the 70 billion one for the target model, right? So they are trained on a very different number of tokens. The 70B might be trained on 5 to 8 billion tokens, and the 3 billion one would be around 1 to 1.5 billion. So what kind of a data set would we need to, align both the draft one and the target? Just for an example.
Yeah, so I mean, it's a very different question if you're talking about, you want to host like a general serving service. This is where you just want to sort of encourage like general alignment between the target and draft model, and this is a really hard and expensive problem to go into, and there you're probably best served by having like, setting up a distillation setup where you freeze the weights of the target model, your larger model, and you're trying to update your draft model just based on sort of general data that you're passing through both of the models, and you want to align the output of your draft model to be as close to your large target model. And this gets really complex. There's not a lot of good software to do this. It can be pretty difficult. Towards like making custom models, like this is where like, if you know that you're just going to be offering maybe like a code completion API or something that's maybe more structured in output, or has some like fine-tuned like company data where you want to or RLHF data where you want to have the model acting in a certain way. This is just kind of towards like, you want to fine-tune like both of these models together. Like you don't want to say, if you're fine-tuning your Llama 70B and deploying this as your service and you want to use a draft model, you should take a draft model and then also fine-tune it on the similar data. So I think it's not so important that the models are pre-trained or initially set up with the same amount of tokens, but more that there is some common tokens at the end or close to when the model is being deployed that, hopefully like relate them to each other. And the best way to do this is whether you're fine tuning or doing sort of general kind of retraining or realignment is distillation. But this is definitely a hard thing for people that aren't researchers to get going. So I can say in Neural Magic, we're definitely trying to build better like tooling around this for our clients, but it may also be like more straightforward if you have like a very specific use case to have one of the methods like Medusa or Eagle, where you're just adding essentially like a few extra projection layers and fine tuning or continuing to train that model or continuing to train those extra layers to essentially add like extra prediction heads on that model. So essentially your job will be much easier if you're just targeting a specific use case or like a fine-tuned use case. And if you're trying to make sort of a general draft and a target model, I think this is pretty hard and still kind of a research problem.
Yeah, you were on spot with the target specific case because we are, trying to speed up the LLM on a very specific data set or very specific task set. That's for structured output. So any academic or any academic, if you know of available that we can.
Yeah, it's a little hard to make you out, but I think you said you're working on sort of a specialized data set. So definitely fine tuning all the models, and if you can, sort of distillation to tie the outputs or particularly the output log props from the target model to try and connect that to the loss of your draft model. So you're updating that with a softer and smoother update function rather than just discrete token signals. Okay. Well, I think that's pretty much it for now. Thanks everyone for joining. And definitely I'm looking forward to the upcoming office hours, and hope to see you there. Have a good day.